just talk a little bit about the continuous prior. Maybe we get to introduce the beta distribution a little bit for the remaining time. So remember, this is the setup that we have just now for the discrete prior. We have 6 possible values. We assign associated probability for each of this, and then we make sure that the list of probabilities satisfies the 3 axioms of probability. And then you do Bayesian base tables through Bayesian crank, all that kind of functions, and then we came up to this. My question for you, especially now, is you know that we're trying to talk about continuous prior distribution, which is a beta distribution that we'll be able to cover. But there is such a motivation of why we want to do continuous instead of discrete. So I guess my question for you at the moment is, based on this table, well, the table is right, like we know it's following the Bayes rule, but do you see anything unsatisfactory in terms of the particular inference that we're doing? In a sense that you think the discrete prior that we used might not be, I would say, satisfactory or might not be comprehensive enough, in a sense. Okay? So pause for a couple of minutes. Anyone wants to share what you think is probably not satisfactory at the moment? Yeah.
You said it just doesn't really capture all of the possible values because, like, for instance, we can't really talk about like 0.35 or numbers that are not included in our finite set.
Exactly. So one thing you notice here, just like by looking at the table as well as like going through the Bayes rule step by step, you notice that if a particular value of p was not specified in your prior, it would never appear, right? Because by Bayes rule, we know that you're updating according to the choices of p that you have. So for example, 0.35, it was not specified in our prior, so it will always be assigned to be 0 in terms of the prior and then the posterior probability. Okay? Yeah, and also I guess not only in between those choices, but also, well, what if like 0.1, right, or even smaller? And when we talk about, say, a list of all possible values for a proportion, it's really anything between 0 and 1. Okay, so that I think will give us the motivation to think about, well, maybe doing a discrete prior is not sufficient because you're just going to miss all of the other possible values that is possible out there. And we're trying to figure out if there's a way that we can do a distribution for the prior that is more comprehensive. In this case, will be a continuous prior covering the entire space between 0 and 1. So one choice will be, we talked about it in the probability review, is a uniform. You remember, uniform between 0 and 1. That covers any possible values, right, between 0 and 1. I'm showing you the density PDF here. So it is a continuous, covers all of them, all of the possible values. But I guess the drawback here is that a uniform distribution is saying that any value is equally likely, right? So that's a very special prior distribution. This continues, so it's better than before. But it's special in the sense that I always have to I'm sort of stuck with all of them are equally likely. So it's possible that, well, I think 0.5 is more likely than any other value. So how can I make a prior distribution expressing that kind of opinion? So the distribution that we're going to cover in this course for any proportion, a random variable between 0 and 1, is a beta distribution. So let me just show you really quick. And then on Thursday, when we come back, we're going to talk more about this beta distribution to get started. So the beta distribution has 2 parameters, A and B. Okay, so let's just keep them in mind, A and B for now. And it is for a random variable between 0 and 1. So beta distribution is a really suitable distribution for proportion. So the 2 parameters, A and B, we call them shape parameters. It's just notation definition in this case. And the density function, I'm just going to cover this really quick here, is that if P follows a beta distribution, then the PDF, remember it's a continuous distribution, so we talk about PDF here. The PDF is 1 over beta function, AB, don't worry about it now. And then P raised to the power of A minus 1 times 1 minus P raised to the power of B minus 1. And this BAB here is a beta function. In order to compute it, you will need to know what a gamma function is. But so don't worry too much about it. You will see that later. Those are considered as constants when we're deriving the posterior. Okay, so just know for now that those are particular constants because, well, you can see that beta function depends on gamma function, but then gamma function, in this case, you need to know what A and B is. So if we fix A and B, those are constants overall. Okay, but we do want to cover the PDF itself. So you will see it over here. And the probability density PDF function PDF follows this particular expression in equation 12. And before we break, I just want to show you that the continuous uniform that we covered is a special case of beta when A equals to B equals to 1. Okay, so this is good to know. So that's why later we're going to mostly work with beta distribution. We're going to see some good properties of this beta distribution for the binomial likelihood. And then whenever we work with uniform, it's better to work with beta 1, 1. They're equivalent. Okay? The beta distribution is much more favored when we're dealing with Bayesian inference proportion. Lastly, this is just 9 different curves of beta. And I label those A, like the two shape parameters A and B in each of the graph. And you can see that, well, by changing the values of A and B, you can have a lot of different types of shapes, right? And then all of the shapes represent a particular prior belief that you might have. So on Thursday, when we come back, we can spend some time talking, like select a few beta curves and just discuss what they represent, okay? And then we're gonna move to, well, this is the prior distribution. How are we gonna derive the full series? Right, good. And don't forget, I think the first homework is due on Thursday. I have office hours tomorrow, but